All right, let's solve the 12th day of Advent of Code in God's Temple. Here we go. Okay, passage pathing. With your submarines, subterranean subsystems, Jesus Christ. The only way you're getting out of this cave anytime soon is by finding a path yourself. Not just a path. The only way to know if you found the best path is to find all of them. Fortunately, the sensors are still mostly working, and so you build a rough map of remaining caves, your puzzle input. For example, okay, start A, start B, A, C, A, B, and the end. Okay, so we have like a graph, some sort of a graph in here. This is a list of how, I think it's like an edge list or adjacency list or something like that, yeah. This is a list of how all of the caves are connected. You start in a cave named start, and your destination is the cave named end. An entry like B and D means that the cave B is connected to the cave D. That is, you can move between them. So the above cave system looks roughly like this. Your goal is to find the number of distinct paths that start at start and end at end. And don't visit small caves more than once. There are two types of caves: big caves, written in uppercase like A, and small caves written in lowercase like B. It would be a waste of time to visit any small cave more than once, but big caves are large enough that it might be worth visiting them multiple times. So all paths you find should visit small caves at most once, and can visit big caves any number of times. Given these rules, there are 10 paths through this example cave system. Okay, that's cool. That is very, very cool. All right. Each line in the above list corresponds to a single path. The cave visited by that path are listed in the order they are visited and separated by commas. Note that in this cave system, the cave D is never visited by any path. To do so, cave B would need to be visited twice. Once on the way to cave D and a second time when returning from cave D. And since B is okay, I don't care about this kind of details. Here's a slightly large example. Okay, so DC end, HN start, KG. So the name of the caves can actually have multiple letters, I suppose, right? There are now paths through it as follows. Okay, so that's cool. Finally, this even larger example has 226. Metis F777. Thank you so much for 36 months of tier 1 subscription. Thank you, thank you, thank you. 3 years. Thank you for such a long support, and welcome back to our HolyC club. That's right. Okay, so there is even larger example, has 226 paths through it, and here it is. How many paths through this cave system are there that visit small caves at most once? All right, so we have a couple of samples in here, right? So which is rather interesting. So let me take a look at the size of the puzzle input, right? So okay. That is a bit underwhelming, but okay, that is totally fine. That is in fact totally fine. I wonder if I can visualize this thing with a graph viz, you know? So yeah, unfortunately there is no like graph viz in TempleOS, but I can write a program in HolyC that converts this entire thing to dot file, and then I can process that dot file outside of HolyC. So this is one of the things we can do. So just to see how the entire thing looks like, I think it's going to be useful, maybe. So, okay, so this is the sample, and let's actually go ahead and start the new day. So this is going to be new day 12, and first I have to provide the image, of course, and the 12. Okay, so we have to provide the sample. So in our case, I suppose the sample is good. I didn't want to save anything. Okay, so I'm gonna copy paste this thing in here and then save everything and quit. And we need to provide the input. Okay, so I already have it open, but whatever. Cool. And save it and quit it. There we go. So let's run AoC, a virtual machine. Let's take a look. Let's take a look. That is very, very interesting. So this is the main. So if I take a look at the input, so here is the input. If I take a look at the sample, this is the sample. Okay, so we can actually chop everything like by lines, and each individual line we can chop by dash, and that way we can basically parse the ends of this entire thing. So while SV size is greater than 1, the thing we're going to be doing is the following. So we already have a SV, so I need a line. So in here I'm going to be doing SV chop by delimiter. I provide the pointer to SV, then I have to provide the delimiter, it's going to be the new line, and then I actually provide the output. So there we go, we have a line in here. So the next thing we need to do, we need to chop by the dash, and to chop by the dash we have to have another string in here. Right, so this is going to be something like, you know what, I think I'm going to call line A, right? So this is going to be A, and this is going to be B. So I'm going to explain why in a second. Right, so basically chop it into A, and then I chop by delimiter A by the dash, right, and I save it into B. Right, so that way B actually contains the beginning of this thing and A contains the end. So that means I need to swap them in here. So I'm going to be doing it like this. B, and I'm going to do that into A. So now A contains the name of the beginning of the one edge, and B contains the end. Right, and we can try to print them, I suppose. So maybe we can go ahead and print the dot format right away, right? So we can do something like dgraph. Maybe not necessarily dgraph, because it's like not directional, I think. I think it's just graph, and we're going to call it caves, right? So this is going to be just like a new line in here, and then we're going to do something like this. Just a second. I'm a robot. Thank you so much for 26 months of tier 1 subscription. Thank you, and welcome to our epic HolyC club. HolyC, thank you so much. That's cool. Okay, so let's go. So, and in here, what I need to do, so the names are actually, you know, valid graph viz names, so I can probably do something like print SV is going to be A, and then I have to do this thing, and then print SV B, right, and then I can do something like this. So that should create a valid dot file thingy, though I would like to also like maybe indent it a little bit, right, by 2. And if I try to run it, so here it is. But I'm not sure if you have to put 1 dash or double dash in there, so I don't quite remember. Graph viz graph. Graph viz graph. So examples. I want to see an example. So there is a gallery. Gallery is probably useless because they're trying to show off very complex things, and I don't really need very complex things. In fact, I need something like this, right? Will you show me the example in here? So you have to put double dash in here. Okay, thank you very much. Okay, so that means I'll have to do something like this. Okay, so that looks like a graph, and let me go ahead and just like copy paste this entire thing. And as far as I know, this is sample, right? So this is sample. I can do sample dot, right? Sample dot. I think TempleOS is going to complain about that one. Yeah. Okay, and then I'm gonna save that, and I'm gonna exit this entire thing. So let's quit this entire stuff, right? And I want to mount AoC 2021. There we go. And in MNT, if I go into the home, AoC 12, right? So here's the dot. So I should be able to do dot t svg, and then I'm going to provide sample dot. There we go. I think it kind of worked correctly, but at the same time, there is a syntax error at line 21. I'm not sure why. So 21. Oh, yeah. Thank you, TempleOS. Very cool. Yeah, of course there is a syntax error in there because it stuck the position of the cursor. So that symbol is created by TempleOS and it just indicates the last position of the cursor. So the TempleOS can recover it when it opens this file again. It stores this kind of information within the files. That was a very good idea. Thank you, Terry. Very cool. Okay, so, and as far as I know, you can provide like big O flag and it will... Okay, so I'm starting to develop TempleOS reflexes. Instead of ls-l, I actually typed dir semicolon. Okay, there we go, and we have a SVG. So if I do chromium sample.svg, we can take a look at this entire thing. So this is basically the sample. Nothing particularly special, to be fair, right? So nothing particularly special, I would say. But this is just a sample. I would like to have something like input as well, right? So let's actually try to render the input. I'm gonna go back super quick and I'm gonna run AoC 2021. Because the most useful information is going to be in the temple, and maybe it's something, it's so small in here we can come up with like dumbest solution possible, right? It's always fun to have a dumbest solution. So I want to kind of like save this thing somehow, but at the same time it's a little bit painful in TempleOS, right? It's a bit painful in TempleOS because to save, you cannot just like append to a file in TempleOS, if I remember correctly. You can just like take a single string and write that string into a file. So that means you have to first render everything into some sort of a buffer and then save that buffer into a file, which is really inconvenient, but I mean, this is how it's done in TempleOS. So you do file write, right? So this is how you write a file. And I think that's it, right? So if I go into write and actually go into the place where the file is located, I don't think I'm gonna find anything useful, right? Maybe there are other... Oh my god, this is blinking so much. I really apologize for the blinking and stuff, but it's just like TempleOS being TempleOS. Right, so there's nothing much you can do. Yeah, there's only file read and file write. You can just read a string from a file and write a string, so there's not that much you can do in here. So unless like you pre-allocate some sort of a buffer and you append a string into that buffer, right? Which is probably fine. Let me take a look at the file write. So what kind of things it accepts? What kind of things it accepts? It accepts buffer and buffer size, which is fine, right? So we can pre-allocate some sort of a buffer, right? So I'm gonna have a buffer, and this is gonna be a buffer capacity. Right, so, and the buffer capacity is going to be something like buffer capacity. Let's pre-allocate maybe 4 kilobytes, because why not? And what we're going to be able to do in here, maybe, we need an operation that appends to that buffer. Also, we need to keep track of the size of the buffer. So this is going to be buffer size, and initially it is 0. So here we're going to have something like buff append. And here we're gonna accept, so I would like to call it a buffer, but buffer is already taken. So I probably have to call it something else. Right, I probably have to call it something else, but I have no idea how to call it, but buffer 0, okay, I don't care. So, and then we're gonna accept the buffer 0 like size. So, and that will append this entire thing in there, hopefully. All right, so how are we going to be doing all of that? If buffer size plus buffer 0 size is less or equal to the buffer capacity, we're going to allow that. Otherwise, we're not going to do that. Though, okay. Yeah, we're not going to do that. So because it's too much for me to think about it right now. So, and then memcopy, I want a memcopy buffer plus buffer size. So this is the destination, the source is buffer 0, and we're copying buffer 0 as z. So we could probably truncate that thing, but that means that I have to think how to do that. Right, and it's just like easy for me to not allow if it overflows, and like I just don't want to think about that. Buff 0 as z, and there we go. So you just append this entire thing over time. So, and then maybe we can have something like buff append null, right, which accept a null terminated string, and it's going to be implemented in terms of buff append, right, buff append s and strlen s. There we go. So something like this. So, and essentially we're going to do buff append null. Right, so this is going to be this thing. Another interesting stuff is that we can, all right, so this is going to be buff append null. It's this one. Here we need to do just buff append. Buff append. Buff append a begin a size. Right, so it actually makes it a little bit painful to work with, but that's okay. No pain, no gain. Buff append null. Right, so this is going to be null, and this one is going to be buff append null. It's actually not null, just append. Begin b size. Buff append null. Okay, holy shit. So after that, you should be able to just write that into a file, right? So file write, and I forgot how to do that. Let me take a look at this thing. So first we provide the file name, the buffer, and buffer size. Okay, cool. And this one is going to be basically graph dot buffer size. Cool. Holy shit. Okay, so now I want to switch to the actual input, right? And I'm going to run this entire thing, and it does not compile. Obviously, that was kind of expected. So let me take a look at 28th line, and in here we have a couple of unused things. I'm not sure what exact. Okay, so there's this thing. We don't have to do that. Okay, so it kind of worked, and let's take a look at what it created. So it's supposed to create graph dot, and it kind of did. It's not a text file, which is totally fine. So I suppose it is basically the actual input, right? So it is input, it's qi ud, and in graph dot we have qi ud. Okay, that all makes sense. So we have a thing that sort of like, you know, adds this stuff to a file, right? So this is how you write to files in TempleOS. You cannot just open a file and append things to it. First, you need to collect all of that into the buffer, and then you have to write it. Maybe there is a better way to do that, but I couldn't find that. There's no obvious better way to write to a file, right? So yeah, if you know what I mean. Okay, so let's go. Just a second. Zero Nal Carnival. Thank you so much for tier 1 subscription. Thank you, and welcome to our epic HolyC club. Cheers, by the way. Alrighty. So let me do it like this, and I'm gonna mount AoC 2021. So MNT home, right? So AoC 2021 12. And here's the graph dot tsvg. Let me double check if TempleOS didn't create any weird symbols. Okay, that's fine. Dot tsvg o graph dot. Okay, and then chromium graph dot svg. There we go. So here's our input, right? Here's our input. TF. So these are basically big caves. These are the big caves. Cool. Very, very cool. So if I understand correctly, the big cave is basically all of the capitals, right? Capital, big, okay. There are two types, okay, big case written in uppercase like A, and small case in smaller case. Okay, that's cool. Cool. So now I'm gonna run AoC and let's try to actually solve this entire thing. I just thought that maybe by visualizing that with graph width we're gonna gain some sort of interesting information, but nah, we didn't really gain anything. So I'm gonna do AoC 2021. But that was interesting. So we exercised how to write into the files. So that was definitely useful in my opinion. All right, main.hc. And we probably need to represent this entire thing somehow. JD Bodio subscribed with tier 3. Thank you so much for tier 3 subscription. First subscription and instantly tier 3. Thank you. And welcome to our epic HolyC club. That is very powerful. Very powerful. Okay, so the question is, like, how are we gonna do all of that? Right. So it's not particularly convenient to think about the graph, to represent the graph the way they gave us, right? So it would be probably better to, you know, I don't even know, right? So we need to understand how many of the vertices we even have, right? So, and maybe we can represent the entire thing as basically adjacent table, because it feels like the graph is rather small, so we can probably do that like as adjacency. And on the intersection, we can store information whether it's a big cave or a small cave. Yeah, that's actually pretty cool. But we need to know how many of these things we have, right? We need to know. And the easiest way to know that would be to maybe just, you know, collect them into the list and remove all of that, but I'm not quite sure. Well, to be fair, okay, I have an idea. I have an interesting idea. What if I just take this entire thing and basically query replace dash with a new line, right? And then essentially I'm gonna sort the lines, right? So there we go. I sorted the lines, and I suppose I can just like use unique lines. Do I have something like unique? But there should be something in there, right? There should be something in there. I'm thinking in Emacs there is an ability to take the selection and pipe it into some sort of shell command, and then take the output of that shell command and copy paste it back. But I can never remember how to do that. It's just so annoying. Like it has like a really weird combination of keys, and I can never remember how to do that. So I think you can probably do a prefix. Right, and then shell command on the region. Okay, so and command on the region is going to be unique, right? This is how we can do that. Okay, so I think I kind of like vaguely remembered. So that's pretty cool. And I wonder if I can like replicate the whole process, right? We query replace dash with a new line, right? Then we sort all of the lines. Then we take this thing and we do shell command in the region, we use unique things, and there we go, we've got the unique things. Can your Vim do that? Probably can. Okay, and then I can say, okay, there is 13 lines in here. 13 by 13 is essentially, yeah, nothing. It's just like more than 100, and it's like very small. It is in fact very small. So what's going to be the start and what's going to be the end? So the start probably has to be like 0 or whatnot, right? The start definitely has to be 0. Then anyway, so let's actually do that. Let's actually do that. When we encounter end, it's like really unclear how we're supposed to like update all of that, because if I want to use end as the last number in position, I don't think it's going to be particularly convenient. So maybe end has to be something special. A goes into the end. Yikes. Well, we can probably pre-process, like we can collect all of the pairs into some sort of a list, figure out how many of these things we have. Another interesting case, is that the same for this sample in here, right? So here I have, I don't know why it takes me so much time. It's just like, it's a little bit annoying, right? The representation of this thing is just like a tiny bit annoying, and that gives me a little bit of anxiety, right? So I cannot just like conveniently represent this thing. Of course, it has to be something like this. Right. And for the sample, it's a different amount of things, right? So this is the sample then. Right, it is the sample. And if I query replace the dash with the new line, and then I sort the lines, and then I do shell on the region, unique. It's a different amount of things. It's a 10 by 10, and yikes, don't like that. Don't like that. It's just so that means basically I need to first read all of the pairs, figure out the amount of those pairs, right, like unique amount, and then know what's the end. But do I really need to have the end as the last thing? So I can probably set end to 0. Okay, so the index in the table 0 is going to be the end. 1 is going to be the start, right? And the rest of them is going to be as we get them. Okay, so that's probably going to be the convention, but maybe it's going to change over time as we like progress in solution. Right, so okay, so we're going to have some sort of a table. So this is going to be a graph, and we're going to have like a graph capacity by graph capacity, right? So, and here we're going to have graph capacity. So it's 13. Let's actually put something like 16 in here. Right, and in here we are going to have some sort of a number, right, which indicates whether there is connection or there is no connection, and what kind of, well, though we also have to keep in mind some other stuff. All right, that's fine. So this thing should indicate whether there is connection or there is no connection in here. Okay. So, and we also need to keep track of the vertices, right? And we need to keep track of the vertices. So I probably have to keep track of them like this. So this is going to be verts, and this is going to be graph capacity. Oh, since I know these are the vertices, might as well actually call them vert capacity, right? It's more of a vert capacity. So graph cap is going to be vert cap. And I want to replace this entire thing, so I'm going to do that, and there we go. So, and this is vert names, but it's too much to type, so I'm just going to call them verts. And then we're also going to have something like I64 verts size, which is initially like 0, but we should probably initialize it in here. Okay, so... Let me quickly remove this entire stuff. So I don't think we'll need this thing anymore, right? So at least for now, it was interesting experiment, but we're not gonna keep it. All right, so we're gonna start with verts sz equals 0, right? Verts sz equals 0. First thing we want to do, we probably want to be able to query the index of the particular vertex, right? So this is what we want to do. Index vert index, right? So, and we're going to provide the name, and essentially it will just return an index, and that way we can probably do the following thing. We're going to do graph vert index b. Interestingly enough, I think it's a bidirectional thing, so that means we probably have to do that the other way around as well. So let's actually introduce the indices for A and B. So I64, it's A IDX, and then B IDX, right? So A IDX is going to be vert index A, and then B IDX is going to be vert index B, right? So, and we're going to do all of that both ways. I'm not even sure if this representation of the graph is going to be useful for this entire stuff, but maybe it will be, who knows? Right, so this is going to become true. Interestingly enough, we need to memset this entire thing. So let's actually memset graph to 0, size of graph. There we go. So we set vertices to 0 and then we reset the whole graph. And here we have to repeat the other way around. So this is going to be graph A IDX and actually B, right? So this is going to be B. A IDX is going to be true. There we go. So the question is how we would implement the vert index, right? I64 vert index. And we're going to accept a name in here, right? So this is basically a name. All right, return -1, whatnot. And we have to actually pass all of that by a reference. So essentially, we're going to look up if that name already exists in the list of the vertices. And if it does, we're just going to return the corresponding index. But if it does not, we're going to basically allocate that new vertex and actually append it in here. Right. So yeah, as you query the vertices, you essentially also add the vertices to the list of the vertices. And that's why I was thinking so hard how to represent this entire thing, because like this is what I probably need, but I'm not sure, right? So I will need to think about this kind of stuff. Anyway, so let's actually start iterating. So this is going to be that, and for I equals 0, I less than verts size, plus I, and we have no way to compare SVs. Nice. So this is a very good problem because it hits so many spots for me, right? So I need to do things that I never done before in TempleOS. This is actually pretty cool. I wonder how you can do that. So let me see. Is there something like memcmp? There is something like memcmp. Right, so we can probably use that, but memcmp is supposed to have chunks of the same memory. So the only thing we need to do, we need to confirm that the strings are equal, right? SVs are equal. So we're gonna create something like Boolean SV SVEQ, right? So, and it's gonna just accept A and B, SV and B. There we go. And in here, if wait, do ends like conjunction and disjunction in HolyC short circuit, do the short circuit. There is strcmp which works on null terminated string, and SV is not a null terminated string. Okay, so are they short circuited? So let me see. HolyC short circuiting. I forgot how to spell circuit. We can always check that, right? So you can always check whether it's short circuiting or not by maybe, I don't know. I don't really know. So let me see. I'm gonna create a new thing in here. So this is gonna be short HolyC. Right, and we probably want to create some sort of a function foo, which simply produces some sort of side effect, but maybe it doesn't matter, right? So it should return maybe false, right? It should return maybe false. And another one is gonna... I really hope TempleOS is not gonna try to optimize this shit. So it would be kind of annoying if TempleOS would try to optimize that. So if I have foo or bar, all right. So, and probably need to wrap that into some sort of a main, right? I need to wrap that into some sort of a main, right? And UF main. Okay, what do we have in here? It calls both of them. As you can see, it does not short circuit this OR, because it first calls this thing, then like saves this result and calls bar. It calls both of them. So we can't rely on short circuiting in TempleOS. It's actually kind of cool. Right, so you don't even need any like reference guide or anything like that, or like manual. If you're interested if a particular feature of the language works, you can just try to use that and look at the assembly, right, and just see if it does that. Apparently it does not short circuit. Or will not short circuit in this case only, and will. Well, in any case, it's just safe to assume that there is no short circuiting. If you just assume that there is no short circuiting, you're never gonna fail, right? So it's as simple as that. Okay. All right. So it's kind of cool. For example, in Ada, by default, also there is no short circuiting, and for short circuiting, you have to use separate operators. It's actually kind of cool. So you have to explicitly say that you want a short circuiting or not. Wait, why would there be short circuit when they both return false? Okay, so you're basically assuming that the compiler looked into the functions and optimized things out. But if it optimized things out, why didn't inline the functions then? So there's a lot of interesting questions in here. As I already said, it doesn't really matter. It's just at this point, if there is any slight uncertainty, even like slightest uncertainty in the presence of short circuiting, just assume that there is no short circuiting and everything's going to be fine. It doesn't matter that maybe in some cases, blah, 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 that doesn't matter. Slight uncertainty, just assume that there is no short circuiting, you're safe. It's as simple as that. There's nothing to discuss in here. Okay, so, and by the way, apparently I pressed Shift Escape yet again, and that didn't save any of my changes regarding the representation of a graph. Yikes! So I got used to the feature of the like modern operating systems that if you try to close with a board, it will ask you, do you really want to quit without saving? That I never actually noticed that how useful that feature is. It's really interesting. So I always thought that like these editors constantly asking, do you really want to quit without saving is really, really annoying. But you take that away and this is what you end up with, right? So this is what you end up with. But it's not like we didn't really lose any progress, right? We didn't really lose any progress because the progress is also figuring out what you need to type, right? So by typing something, you also figure it out what you need to type. But once you figure it out once you need to type, you can retype that faster, right? Because programming is not only typing, you know. Right, so we didn't really lose much, right? So I just need to retype whatever we figure it out we need to type. Does it make sense? So, all right. So let me see. Just every time you want to quit, make sure you aren't on shift. Yeah, just get a house. What's the deal with homeless people? Okay, so let me see. So we have to do something like define vert capacity, and we're gonna have 16 of these things. So this is gonna be Boolean graph vert cap sv verts, and it's gonna be vert cap. Right. So as you can see, I don't think about this kind of stuff anymore. I just retype in this thing. It's just gonna be sv. Right, and on top of that, I need to do I64 vert index, where I have to provide the name of this entire thing. Right, so here is the name, and we also need to do something like Boolean sveq, which accepts two things in here, svb, right, and also something like this. Cool. So I also need to control like save periodically as well. So I need to I64 A IDX B IDX. There we go. Then A IDX vert index A. bidx vert index b, graph aidx b idx true, graph bidx aidx true, well, the other way around, but I typed it correctly anyway, whatever. So also I need to set vertices to 0, and then I need to memset the whole graph to 0 as well. So it's going to be graph, and let's make sure we saved everything. I'm going to press Ctrl S several times just to make sure that everything is saved. I'm going to press escape and open it again. It's there. We didn't lose that progress this time. Very, very cool. I'm super happy. Anyways, so what I want you to do in here is just like compare their sizes. If they have different sizes, we can quite safely say that it is not correct, whatever. All right, so size, if size equal b size, right, we're gonna do memory CMP, right? So Cyberdyne, yeah, thank you so much for a Twitch Prime subscription, for 9 months of Twitch Prime subscription. Thank you, thank you, thank you, and welcome to our epic HolyC club. So it's gonna be memcmp, and let me take a look. So I'm gonna just take a look at what we have. So point-to-point account. Okay, that's cool. So the first one is gonna be begin a size. There we go, and it has to be equal to 0. Otherwise, we're gonna automatically say that it's equal to false. Cool. So, yesu, kawaii freaking desu. So, Control S, I64, equal 0, less than verts size, plus I, right, and if SV equal name to verts I, and we have to take a pointer to that thing. We're gonna just simply return I. There we go. So RTNA, thank you so much for Twitch Prime subscription. Thank you, and welcome back to our epic HolyC club. Okay, so essentially, we're only gonna reach this point. When we don't have that vertex in there. So what we essentially have to do, we just have to, I suppose, do verts as z plus and assign the new name in there, which also indicates, right? We only have the pointer to that thing. We need to copy, right? We need to copy the name. So we have to do something like mem cpy. For a second I forgot. So this is the destination, this is the source, and we have to provide the size of sv. Right, it's not really gonna copy the whole string, but it's gonna copy, essentially it will move that string like inside. If that makes any sense. We're moving this thing. So move semantic and HolyC. Did you know that there is a move semantic in HolyC? It's amazing. All right, so, and then what we have to do, we have to return, I suppose the way we can do that, right, I can just like do it like that, and then return verts as z plus. Cool. So there we go. That's basically it. And we can now print the information that we managed to gather. We know how many vertices we have. So we can say red d verts, and we can do verts as z, right? I think it's verts as z. And then we can dump the graph, right? So let's actually do something like dump graph, and we'll just dump the table, right? Well, let's just dump the table. We can also maybe dump it as a dot. Yeah, so we can actually take our code that dumps the dot thingy, and yeah, but maybe later, not right now, because we still have the code for the buffer, right? So we can use that thing for the dot thingy. All right, so let's go. Oh, by the way, to do move sveq to common.hc, right? So u0 dump graph. And I'm gonna just do it like that. So let me see. So I need to I64, I and J for I equals 0, I less than verts as z plus plus I. So, and I probably need like a new line in here, so I have to wrap it in this stuff. So here's the new line. And then for j, j less than verts as z plus plus j. And this is gonna be, I don't know. Can I use Boolean? Probably D. Let's actually do something like D. And so then I'm gonna use graph from I to G. Can you move from I to G? Okay, so if I try to run this entire thing, it does not compile. Let's take a look at where it failed. It failed in here. Let's quickly fix that. There we go. So this is basically the representation of the graph. This is actual input, right? So this is actual input. Though maybe it would be nice to pad these things a little bit, right? With a little bit of space. So let's actually put 2. This is not what I wanted. Let's put 2 in here, and if I run it, okay, so there's a little bit of spacing in here. I'm not sure if it helps with the readability, but I mean, it's just not that compressed anymore. So yes. So we can also add like additional new line. Now it looks even better now. Would you look at that? It looks even better. If you add additional new line in here, right? Additional new line in here, it looks like it's padded properly. That's very cool. That is very cool. I wonder, like, the terminal supports like different colors and stuff. Maybe we could like render them with different colors, but I'm not sure. But there is a way to like color things differently. Anyway, so let's work on this sample, right? So the sample is a little bit smaller, so it's a little bit easier to work with. And another interesting thing is that we also need to distinguish between the big caves and small caves, right? So, and the easiest way to distinguish between small and big and small caves is to look at the characters, I think, right? So imagine that you have an index I, and we can just do verts I, then begin 0, and you need to check whether it's a capital letter or not. So there's a little bit of a code, but maybe we can wrap that into like a small neat function. The question is, does TempleOS have things to check whether something like uppercase or lowercase or something like that? I remember having something like lower. It has 2 lower, right? Or it had 2 upper. It does have 2 upper. This is really weird, right? It does have 2 upper, but it doesn't have 2 lower. It doesn't have is upper, and it doesn't have is lower. It's just like has 2 upper. Probably because Terry never needed any of the other things. So he only needed 2 upper, so he just implemented 2 upper. So we'll have to implement the rest of the stuff. Right. Is the %2D a formatting thing just in HolyC? No, it's also in C. You can try that in C as well. Okay, so let me see. We can now do something like this. Is big, and we're gonna accept the index. Maybe vert, right? So this is the vertex. And in here, we just take the vert, begin 0. And maybe we want to save that in here, something like this, right? So, and then we can just check there we go. So something like this. So, and I think that's the easiest way to check that. Is big, is small, is big. Alrighty, so X is unused. What the hell are you talking about? Oh yeah, I remember this one. Okay, so maybe you have to do something like I64. Wait. SV. Right. Yeah. Wait. Yeah, I64. You have to do I64, so that's fine. So, like, for some reason, HolyC doesn't like when you allocate on the stack these kind of variables because they're too small. right, and basically it will just warn you that it's using 64-bit for that register variable instead of like 8-bit. So maybe we want to be explicit in that regard, if that matters even. Okay, cool. So I think I want to make a small break because I need to pee. Right. And after the break, we're gonna probably just do some sort of like Dijkstra algorithm. What's the proof of the solution? What's the proof of the solution? The proof of the solution is probably like how many paths there is, right? So how many paths there is. But we can probably... I have a weird idea. We can probably try to do DFS. And as we do DFS, we can just keep track of how many things we already visited. I think we can just do a classical DFS, right? So yeah, let's make a small break, and after the break, we're gonna just code the DFS and see how it goes. All right. All right. Let's implement some sort of a DFS. I don't know, and let's go. I think I'm just thinking what's going to be the easiest way. We probably need to... do we need to even mark anything as visited? I think we can just brute force the entire thing. Right, so we can literally just start from a particular thing and just brute force. Will it actually confirm that there is no cycles or anything like that? Cycle, loop. Maybe there's no loops, right? Given the limitations, right? There should be no loops in there. So we can just go ahead and try to go through all of these things. We're going to start with the sample, right? Let's do the DFS. So I don't think it's going to return anything. And we're going to provide the vertex, right? So we're going to provide the vertex. And then I suppose we need to keep track of how many paths we found, right? From start to the end. We're probably going to actually provide it in here, right? Count. And there we go. Interestingly enough, I can probably do the following thing. I64 count initially 0, and then I need to find the vertex of the start. That means I have to do the following thing. I have to take maybe something like a begin is going to be equal to start, right, and then a size is going to be equal to 5. Right, which is kind of interesting, but that's fine. So then I can do something like start. Well, probably can't use that, but that's fine. DFS vert index a, right, because that's the start, and then I have to provide the pointer to the count, right? So that's how we're gonna start in here. All right, so I accidentally closed this entire thing. And then we probably have to print something like part 1 and then the count itself, right? So how many of these things we found. Let's see, out, but count. Right. Though, while we are like doing this entire thing, right, we still need to keep track of the visited things. Just in case there could be loops in terms that you already visited a small case in that regard, right? So there could be something like this. And the small caves may form loops, and that's quite important. So let's actually allocate an array where we're going to keep track of the visited things. So here's the vertices, here's the graph, and we're going to have visited. So it's a vert capacity. There we go. So, and before doing the DFS, we're gonna mem set this entire thing, right? Mem set visited 0 size of visited. There we go. So we're gonna do something like this. Cool. Interestingly enough, we need an indication of the end. Right. We need an indication of the end. So that means we also need to... Okay, so let's actually call this thing something like start. Oh, shit. Star... Start. No. STRT and I64 end. And end, start and end already taken for whatever reason. It's so annoying. Okay. Let's call it A and B. I really don't care. So A is the start and B is the end. So, and because of that, we can do something like this. Alright, so this is going to be B begin, end, and B size equal to 3. There we go. So that way we can actually find that. So it's vert index B, and there we go. So we're going to be basically passing like you know, begin and end. Oh my god. Okay. So what we need to do, we need to start iterating through all of the neighbors, so to speak. I64, it's gonna be I equals 0, I less than verts size plus plus I. All right, there we go. Right. If graph, if you can move from A to I and this thing was never visited, right? Was never visited. So probably I, this thing was never visited. We are going to go ahead and visit it, right? But we're only gonna go ahead and visit it if it's not big. If not is big, right? We're gonna say it was visited, equal true, right? So why did I allocate visited as a two-dimensional array? Can anyone tell me? I think I'm a little bit dumb, right? Because visited is like, it's not the graph thing, it's the visited. We're not checking whether we visited particular, you know, arcs, nodes, edges, whatever, edges, right? So connections, whatever the fuck it's called. I don't care. I'm not a computer scientist. Okay, so it's not big. That means we're gonna mark it as visited, right? And then we're gonna just go there, right? IB. There we go. And we also have to pass the count in there. Should be it. Interestingly enough, we want to check the following situation. If A equal B at any point, right? If A equal B at any point, we have to essentially just increment the counter, I think. Right. So we're gonna do something like this. We're gonna increment the counter, so it's gonna be count plus plus. Here is the interesting thing. So we're doing DFS and we leaving the trail of visited things. And as we backtrack, I think we need to clean up that trail. Right. We do need to clean up that trail. Right, so the only reason why we keep track of the visited trail is that if we found the loop, right, through like small things, we want to kind of backtrack and just like do different things, like, you see? So that means we can quite safely just say visited I false, right? So as we unroll from the recursion, we just like cleaning up that trail. So, and here, of course, we have to probably return from this entire thing. Of course, that's quite important. I think that's the whole DFS that I want you to implement. I hope I didn't forget anything. So should be fine. Should be fine. We can try to test a very small sample, if you know what I'm talking about, like a very small sample that comes starting at here, right? So, and how many? So there are 10 paths through this particular example. Okay, so let's actually try like a very simple sample. Okay, so I'm gonna mount AoC 2021. There we go. MNT home AoC 12. Right, so it's gonna be small txt. So this is a very, very small example. I wonder if we can even like render the trail somehow, like this one. That would be actually kind of cool, I think, but not for now, I suppose. Okay, I'm gonna save that and I'm gonna quit this entire thing. And let's run AoC 2021. Okay, good. Why is it so slow? I have no idea. Don't ask me. For some reason, it is slow. I hate MLOS. Terry, it's such a simple functionality. It's just like I lost so much code because of that shift escape reflex. Oh my god, it's just annoying. Okay, Dominic, thank you so much for 4 months of Twitch Prime subscription. Holy fucking shit. Okay, so so annoying. It's the most annoying operating system I've ever seen. This is just like, holy shit. Okay, now we have to retype it, but at least we already figured out what we need to type, right? So again, so it's not like we're losing much progress. We're only losing the typed progress, right? Because the challenge is not only to type things, but figure out what you need to type, right? So, and this is something that quite often people forget, especially people who are managing programmers, right? So they think the job of the programmer is just to type text, which in reality is not true. Like typing text is actually like a small part of what programmers do. Like the majority of the time, programmers figuring out what needs to be typed, right? So it's figuring out. We already figured out a little bit what we need to type, so we can retype it again. Okay, well, I already said that, so I'm repeating myself at this point anyway. Okay, so if A equal B, right, we know that we have to essentially stop. Right, so this is going to be count plus plus, there we go. And I need to return it here. Cool. So, and then I64I for I equals 0 less than verts cnt plus plus I, right, and then what did I print? Yeah, okay, cool. I'm not gonna say anything. You just have to have like a divine intellect to be able to use this operating system. That's the only thing you need to have. All right, if graph, if you can move from A to I, right? If you can move from A to I, and this thing was never visited, right? Was never visited. So I don't know if visit even exists there, but I'm too lazy to go up there. And if this thing is not big, right? It is not big. We're gonna do visited I true. Visited I true, right? Then DFS IB count, IB count, and then we have to do visited I false, right? So we're like leaving the trail of visited, then we're cleaning up the trail of visited. So that's basically what we're doing. Let me see if I have visited already. I don't. All right, so let's allocate that. Visited vert cap. Cool. Control S, Control S, Control S. Holy shit. Okay. So in Emacs, like if you try to quit without saving, it will just scream all over the place. So, and I kind of got used to that, and apparently that beat me in the ass. Right, that beat me in the ass. So begin is going to be equal to end, right, and B size is going to be equal to 3, and then we're going to do something like vert index B, right? So can I try to, yeah, I want you to put a small thing in there, safe. So this is the small, and now I can do the following thing. I'm gonna try to run that on a very small. Okay, so it doesn't compile, which is great. It's always great when HolyC cannot compile a program, because at least it will give you useful information. Quite often it will just compile whatever gibberish you give it, so which is very horrible, really horrible. All right, so what do we have in here? I don't quite understand what you're talking about. Invalid L value for verts count I. Okay. So is that because we don't have I? We do have I. Is that because we don't have verts count? Is that the reason? It's verts SZ. Okay, so I keep confusing them. All right. So it's verts SZ. Thank you so much. All right. So, and it did a thing, right? It did a thing. And it didn't print anything because I forgot to print that thing. Okay, that's cool. Alrighty. So if I try to do count, right, if I try to print that, it printed 0. That is very, very cool. That is very, very cool. I'm really happy that it printed 0. So the question is, maybe we have to figure out, so what is the end and what is the begin? I64I IDX, vert index A. Right, and then I64B. I already have IDX defined. Okay, of course. IDX vert index B. Right, and here we're gonna have A IDX and then B IDX. Right, B IDX, and I really want to print them. So I'm gonna do something like start. Just want to see if they are correct. A IDX and right, so this is going to be something like B IDX. So let me see. So it's a 10 and 11, which does not make much sense. Okay, let's start with the small. I think I forgot to use the small. Okay, 6 and 7. All right, so that kind of makes sense, I think. No, it doesn't make sense. 1, 2, 3, 4, 5, 6. Yeah, it does make sense. Okay, that's cool. All right, so the count does not really work out. It does not really work out. So we have to also do a very important thing. We have to memset visited to 0. Memset visited 0, size of visited. So this is one thing. And another thing, I forgot to check that I should not be equal to A. That's quite important. I not equal to A. Well, I don't have to do that because they're never going to be connected. Right, so they're never connected in our representation at least. Okay, so we can move from that to that. Then visited becomes true. It's not visited, then it becomes true if it's big, and then we leave in the trail. Okay, so if I try to run this entire thing, it still didn't do shit. But what's interesting is that it stopped at some point, right? It kind of stopped. Can we basically show the trail of this entire thing? So it's going to be vert D A. And okay, apparently it doesn't even leave the trail. This is very interesting. Okay, DFS apparently doesn't even do anything. So it sees that A and B are equal to each other, and then it just sort of like gives up, which does not make any fucking sense. Okay, so all right. So A, then B, B, and A, 6 and 7, if they're equal, it doesn't even try anything in here. This is so weird. Okay. All right, let me actually dump the graph just to see what the hell is going on. So we dump the graph, there's nothing on diagonal, right, so it's like symmetrical and shit like that. So should be fine. So we start as 6th one, right, 0, 1, 2, 3, 4, 5. This is sus. What the fuck? What the fuck is this? Where is the start and where is the end? Where is the start and where is the end? So, did I fuck up memcopy somehow? So destination and source. This is the destination and this is source. We copy in the size, so that should be fine. This is really sus. What the hell? Yikes. TempOS. I know the mistake. I know the mistake. Who can notice the mistake? Somebody noticed that. Okay, I see that. This is so fucking bad. Why is it so difficult to just check whether you mistakenly pass something by a value instead of the pointer? So bad. Oh my god. Terry, I'm really disappointed. I'm extremely disappointed in you. I'm sorry, Terry. But this is not divine intellect. This is not divine intellect. I'm really sorry to tell you that, Terry, but it is not. 100% not divine intellect. Okay, 37, which is probably not correct. Right. Oh, right. So how many do we have in here? So there's the 10 paths, which is definitely not correct. Okay, so let me see. So 0 and 5, and it's just like it found way too many things. It found way too many things, and I wonder if that's because I'm. Why are you doing? Why are you doing that? I didn't ask you to do that. I really didn't. What are you doing? It's holding shift for whatever freaking reason. Okay. All right. I wonder if this is because I'm getting back from the trail. Should I just not do that? I should probably do that. So this is not a correct assumption, that's for sure. This is not a correct assumption. So there's like way too many things in here. So this is a small sample. And let me try to understand. So do I set the count to 0? I do in fact set count to 0. Everything seems to be fine, right? So why would it be not correct? Though, interestingly enough, we can try to print all of the paths, if that makes any sense, right? So just maybe some of the paths are repeating, and we don't want to have that. Okay, so I can do something like print sv. Print sv a. I have to pass it by that thing, and then I have to put like a space in here, and probably at the end in here I have to do like a new line, right? So this is how we're gonna approach this entire thing. And let me see all of the paths in here. That didn't work. That straight up didn't work. I wonder why. Oh, I know why. Because I need to do verts a. This is what I wanted to do. There we go. So these are basically all of the paths. So there's A, B, A, C. And there's like way too many of them. Did it repeat some of them? So what is that? Why there is this thing? I'm not sure about this thing, like what the hell is going on in here? Some of them do look correct, but then at some point it's just like, why do I have ends in here? That's a very good question. I think I know. One of the things we have to do in here before we start the DFS is we need to mark, I think we need to mark visited, like a index as visited already, right? Because when we start, we kind of assume that it is visited, right? That's the thing we probably need to do in here. So if I do that, that was correct. Okay, I found a mistake. So essentially, the entire code just basically assumes when you enter the DFS, when you enter a DFS, the A is already marked as visited. And that invariant was not correct for the start, right? So what we had to do, we had to correct that invariant. Okay, so I see what the mistake that I actually made. And HolyC along with the TempleOS doesn't make it easier, that's for sure. Holy shit. Oh boy, Control S. I mean, I already started it, so I don't really have to save that. Okay, so now it just prints the 10. So I might as well actually not do these kind of things. Right, so let's go ahead and just like unprint this entire stuff. Right, so it just prints 10. And we probably don't need the dump graph. So yeah, and let me quickly do part 1. Cool. So now if I switch to the sample, right, sample, it is 226, right? It is 226, 226, okay, that's cool. And now if I do 0, it is 3856, 3856. Hopefully, let me actually keep it like in front of my face. And I also wanna zoom in just a little bit. I forgot how to, yeah, this is how you zoom in. 3856. 3856. First try got cooler. Bam! How about that? How about that? Yo! So, that's pretty cool. GG. Thank you, TempleOS, for making my experience, you know, simple. I really appreciate that. Cool. Let's do a committee and prepare some lube for the part 2. Git status. So I probably need to do something like sync host, and it's going to be AoC 2021. All right. So we have some stuff in here. So diff. So oh, I don't know what's the difference here. Why visualization here matters, but okay, that's totally fine. So what I want to do in here, I probably want to maybe add AoC 12, right? So there's a bunch of stuff in here which is kind of irrelevant, but I'm going to commit that anyway. So commit add day 12 part 1, right? So then let me take a look at the status, and I'm going to reset -- heart. So let me see if I didn't nuke my installation. Okay, push origin master. Push origin master. Cool. So you can find the source code as usual in the description, or if you're watching live, the source code is available in here if you want to just check it out. So all right, let's take a look at the part 2. So how much screwed up we are now. After reviewing the available paths, you realize you might have time to visit a single small cave twice. Specifically, big caves can be visited any number of times, a single small cave can be visited at most twice, and the remaining small caves can be visited a single small cave later can be visited at most twice. Single small. And the remaining small caves, what is a... And remaining small caves can be visited at most once. What's the difference between single small caves and remaining? Okay, however, the caves named start and end can only be visited exactly once. Once you leave the start cave, you may not return to it, and once you reach the end cave, the path must be ended immediately. Now the 36, like, what? A single small cave can be visited at most once. And I see. During the path, during a single path, you have an opportunity to visit a single cave Okay. So, all right. That is very interesting. Okay, so it's just additional condition and a little bit more time to brute force this shit. Okay, I see. So there's a 36 condition in example above, and okay, the slightly larger number above have now has 103 paths, and the even larger example now 3509 paths through it. Given these new rules, how many paths through this cave system are there? Okay, so it's just like additional dimension, right? So it's additional dimension in the brute force, essentially. The question is rather, would we need to optimize anything? So, right. Adding more dimensions to the brute force is easy. But optimizing and just getting rid of some stuff is just like, this is the difficult part. Okay, let's see. Okay, Okay, main. Alrighty. Let me see. So in here we have a DFS, right? So we have some sort of a DFS. What I want to do, I probably want to extract yet again the reading of the input, right? So let's go ahead and do that. So U0 read input, and I think on top of that, read input should also return the start and the end. I think that's going to be very convenient. So we're going to do something like v start, right? Because start is already taken. V start and v end. But I'm not quite sure if that's very important. So maybe we could make those things like global variables, because why not? Why not make them global variables? I think that's totally fine. Yeah, because it's part of the input anyway. Yeah. So let's go ahead and do that. So it's going to be v start and v end, and then v von Zulu. Okay. Alrighty. So I probably want to copy paste a lot of this stuff in here. So I'm gonna literally copy paste this entire thing and just like remove the things that are not important for the solution. Okay, so we start with svab saved index, blah blah blah. So we do this kind of stuff, then we read the whole graph. We probably don't have to clean the visited count, is not really that important, but A and B is important here. So we'll have to do something like v start and then v end. What's not important here is this one, and this one. There we go. So that's basically everything that I want you to do in here. So that's reading the input. All right, so the first thing we do in part 1 is read input. Read the input. So we don't need that stuff anymore. We do need memset. We don't need this thing, and we don't need this thing. And we do need to set visited to true, right? So this is how we start. And then here we can just do something like v start and v end. And since v end is a global variable, maybe we don't even have to pass it in there, right? So let's actually refactor it. Like I should have actually made it global, like a long time ago. Okay, so this belongs here. This 100% belongs here. Okay. So v start, and this one is going to be essentially just a, right? Just a, and this one is going to be simply v end. And when we pass this entire stuff, right, we can just do it like that. There we go. So all of that information is global anyway. Graph is global, so why not make like start and end global as well? I think that's fair. I think it is rather fair. Okay, so if I try to run this entire thing, it did not compile. Let's take a look at why. Visited. Okay, so this is because we need to mark v start as true. Okay, anything else? Okay, that is correct. That is absolutely correct. Control S, Control S, Control S. Okay, so maybe I want to rename DFS to DFS1, right? Because it's using the condition of the part 1. So I'm going to do Control F and I'm going to rename DFS to DFS1. And of course, we want to replace everything. Replace, replace, replace. There we go. So we have DFS1. Cool. And now I'm going to uncomment this thing and I'm going to start here. Cool. We're going to read the input on the part 2. And we need to prepare the count, right? Because it's essentially the same problem, but with just like slightly different conditions. Let's prepare the visited. We need to set the visited to 0, size of visited. And of course, visited vstart is going to be true. And we're going to use DFS2. DFS2. vstart and count. So, okay, this is quite important. vstart can be only visited once. vstart can be only visited once. So essentially, my idea is simply copy-paste DFS1 with a simple twist, with a simple Boolean flag, right? So, and that Boolean flag indicates whether for the small cave, we already visited it twice, right? So, yeah, maybe, I'm not sure. Yeah, that's gonna be the case, I think. That's gonna be the case. That's gonna be the case. So essentially, and the moment we're gonna assign that flag is when we encounter a thing that we connected to, but we already visited, and it's a small cave, and the flag is not set, right? So, and that flag will also indicate that we already wasted an opportunity to visit a particular thing twice, right? So something like this. Okay, so this is DFS1 and this is going to be DFS2. Okay. So I'm not sure if it's a good idea, but yeah, how should I call this flag? Twice, right? Twice. Okay, I'm just like keep thinking about stuff. So what do we have in here? Just a second. Cool. Now let me see. I suppose you can't visit the start twice, so that's why we're gonna yeah, I mean, yeah, so we'll have to do something like this. So this is gonna be false. There we go. So this is gonna be the end. The end. So this is DFS2. Again, if graph is connected, we probably want to actually go a little bit deeper, right? We actually want to go a little bit deeper in that regard. So graph, like I is connected to A. And here is the next question. Is I big? If it is big, we can just continue moving as usual, right? So might as well actually probably just do, you know, this kind of thing. This kind of thing. So this is going to be is, if it is big, it's going to be one thing, right? So that means you can simply continue executing without like marking it as visited or anything like that. It's going to be just DFS2. And I twice is going to be the same as usual, and this is going to be just the count. Okay, otherwise, if it's not big, we know that they're connected, right? There's another two situations in here. If we already, if we haven't visited that thing twice, we may try to do that. We may try to do that. So let me actually put it like this, right? Let me actually put it like this. Okay. We know that it's already. It depends actually, right? It depends. We need to look at whether it was visited or not, right? We need to look at whether it was visited or not. You know what? I think I want to make a small break, and after the break, we're going to continue doing this thing because I need to untangle my my thoughts right now. So, all right. So this is a very complicated logic. So let's go ahead and implement that, right? So it's just like, yeah, we have to do a lot of if else, if else, if else, and I also realized that you also have to keep in mind that you cannot, you know. Visit vstart twice, and you can accidentally try to do that. So we'll have to be super careful. Okay, if something is big, right? If something is big, gotcha hyper, we can just like move forward without worrying about that. If it's not big, we need to consider, so we know that it's small, we know that it's connected, right? We need to consider whether it was visited before, right? So was it visited before? Is visited. If it was not visited before, right? If it was not visited before, we can quite easily just say, okay, visit that thing then, DFS2. Go ahead and visit that thing. We will need to say that we visited it. Since we know for a fact it's small, we are allowed to mark it as visited, right? DFS2 becomes I. Twice is the same, and count is the same. Count is always going to be the same. And after that, we have to do visited I, right? So this is true. Even like it's only when it was not visited. If it was visited, right? If it was visited, we have to consider another interesting thing, right? Have we already wasted our twice bonus? So if not twice, we can go ahead and try to do that yet again, right? We can go ahead and try to do that yet again. So it's already visited, we don't have to do anything in here. So we have to do DFS2I true count. There we go. So yeah, it's already visited. We haven't wasted it. We marked that we already wasted twice. And yeah, then we're not going to try to do that. Okay, so that's fine. That is very cool. So essentially, every time we found the loop, we are allowed to like visit it again. So, and I think if it if it's visited and we already wasted our twice bonus, there's nothing to do in here. We just like do that. Though, interestingly enough, we have to be careful. We cannot visit vstart twice, right? We can't visit vstart twice. So here's the thing. It's a small, it's already visited. We have a bonus, and I is not equal to vstart. I think that's quite important to consider, because you may actually go forward, then look backward and see that you already visited start, but you have a twice bonus, so you can go back to start. But it was explicitly said that you cannot visit let's start twice. So, and yeah, there is a potential problem that you may start actually going back, but once you step back once, you won't be able to go anywhere because you wasted your twice bonus. So basically that path is going to be broken. So I guess we're kind of safe on that part. So yeah, and it will be also kind of nice to probably compress this entire logic in here somehow. Essentially like this, right? So it's if is big, then else if visited. We're gonna do that. So and then another one else if that, right? And then we can just you know, remove the rest of this stuff. There we go. So that makes it a little bit more compressed, I think. A little bit more compressed. Cool. So, and when we started DFS2, right, we actually started with false, right? We didn't waste any of this stuff. All right, so that's a little bit, so that's the whole modification of the logic, if I understand correctly. That's the whole modification. It's kind of a neat modification, I really like it. So let's actually go to small sample, right? Control S, just in case. And let's go ahead and run it. And it didn't compile. Okay, let's fix the compilation errors. So what do we have in here? Visited, vstart true. There is no such thing as true. There is a big true. Okay. So, and what we got? We didn't get anything because I didn't print the count. Okay. So this one is going to be part 2, D, and I'm going to say the count. And then if I try to run that, it took some time, but part 2 is 4. Nice, nice one. So there's only 4 for the small part. So let's actually figure out what's up with that. So there's a small, there's that, and so let me confirm. Dump graph, right? So this is the graph. There's nothing much to say in here. So in terms of like vstart, let me see if vstart. You know what? We can just like print the paths, right? So let's just print the path and see like what path we found. I think I know. I found an error. Like I was about to print the path, but then I instantly found an error. Okay, cool. Very cool. Thank you so much. Alrighty. So, and I suppose 36. Do we have 36 of them? Right. So there is a 36 for that small sample, right? 36. For that bigger one, we're gonna have 3509. All right. So that's already something. Let's take a look at the bigger sample. 3509. All right. So, and let's see if it's going to actually hog our entire machine. Okay. So that didn't take too much time. It was like 171 milliseconds, right? And that's basically the solution. Okay. So it's 116,692, right? 116,692. Is it going to be first try got Kudra moment? It is! Bam! How about that? Both of the parts are first tried. Isn't that cool? Isn't that cool? I think it's pretty fucking cool. Alrighty. So let's do a committee, and maybe even a pushy. A pushy. All right. So let me see. So I'm gonna just quit everything in here. So git status. Right. Maybe I'm gonna do sync, and I'm gonna sync all of that into the host. AoC. There we go. Okay, just a second. Something is clearly wrong. I forgot my password. What the fuck? Am I already hacked? Apparently not. Okay. So if I take a look at the diff, there's this thing, and this is the part 2. Though I would like to, you know, actually run both of the parts in here. Super quick. So let's take a look. So I'm already in a corresponding folder, so that should be fine. So I'm gonna go in here and let me uncomment both of the parts, and I'm gonna run it, and here it is. Here are both of the parts, which is nice. Okay, so let's sync everything in here one more time, and let me see. So that should be fine. That should be fine. Okay, git status, git add home AoC 12. Add day 12 part 2. And I'm gonna push that right into the repo. Okay, so you can find the source code in the description if you're watching on YouTube, and if you're watching live, you can find the source code in here if you are interested. So it took me exactly 2 hours, believe it or not. Surprisingly, it took me exactly 2 hours. It's like yeah, so that's fine. So it's within my usual streaming schedule, because I usually stream for 2 hours, like I have a time limit. Just not to strain myself too much. All right, I guess that's it for today. Thanks everyone who's watching right now. I really appreciate that. Have a good one, and I see you on the next day of AoC in HolyC. All right. So thanks everyone for watching, and yeah, love you all.